All right, so it is recording now. Okay, so, right, as I said, I will be working with these formulas. So now, so now what I want to do is, I want to go to RStudio really fast. So let me share that screen with you guys. RStudio. Okay, so we've already done most of this. All right, so we've already figured out how to get, so let me erase all of this. So we already figured out how to get standard deviation, variance. So let's do it for our cigarettes and mortality rate data set. So let me just copy this and let me write SD here. All right, so if I were to write SD, again, as always, data set first and then your variable, then I get the standard deviation. Cigarettes is my X variable, so this is SX. And then, actually, let me put the hashtag here so RStudio doesn't think that's part of the command. And then, of course, if I do variance, it's the same thing, except I changed the SD to variance. And then this is the variance of the cigarettes variable. That's SXX. And remember that we can actually take SX and square it. Either you write this or you simply do this. Doesn't matter which one you do. And you see that you get the same. So whether you're squaring it or multiplying by itself, you get the same value as the variance, that using the variance command. So again, this is just a reminder that SX times SX equals SY, oh, so not SYY, SXX. And then I can do the same thing with the mortality rate variable. Oops, that's not what I wanted. Come on, there we go. Sorry, just kept on pasting on here on the console. Okay, so this is, let's do mortality. All right, so if I do standard deviation of the mortality variable, that is SY. If I do variance, then that's SYY. So now let's do that. 114.57, that is SY, and 13,127, that is SYY, the variance. And of course, it's the same thing, right? So I can just simply take this standard deviation value and square it to get variance, right? So it's the same thing, you know, except for some minor rounding differences, right? So it's always the case that SY times SY equals SYY, and SX times SX equals SXX. But now let me show you that SX times SY does not equal SXY, right? So this is the covariance, and these are the two standard deviations. They are not the same thing. So this is my SX value here. And of course, I don't square it. I just want the standard deviation, 311. And then SY is 114 times, so SX times SY gives me this number, 35,658. Right, so this is what I get when I multiply these two standard deviations. And now let's get the covariance, right? Covariance, right? So this is SXY, right? So this is the covariance, and that's the command covariance. And of course, we want both X and Y contained in that command. And so here, if I run this command, I get that at the bottom, covariance is 28,625, which is a different value than Sx times Sy. Sx times Sy gives us 35,000, and covariance Sxy gives us 28,000. So again, this shows you that Sxy does not equal Sx times Sy. Or Sx times Sy does not equal Sxy. All right, so again, as I said, I always spend some time demonstrating this because every semester, this is a problem that is repeated. So of course, if you made a mistake on this, on the midterm, I did not take off any points because I hadn't really gone through this point in too much detail. So that's why if you made a mistake on the first midterm, you got full credit. But on the second midterm, if you do this mistake, then I will be taking off points. Okay, so now we have this, and again, so let me share this document. So this is the PDF document that I will post on Canvas after class ends today. So again, it actually has the calculations, all of the calculations that we are doing today. So here again, I showed you how Sx times Sy does not equal Sxy. And again, I've shown you how Sx times Sx gives you Sxx. I haven't done it for Sy and Syy, but I already did that on RStudio. Okay, so I'm just gonna read a comment. Okay, so covariance of X and Y. So covariance looks at, given that you have observations and each observation has its Xi and Yi value, you are looking at all of the Xi values and whether they are below or above average. So that means that you're comparing Xi values to their means. And then you're looking at the Yi values and you're trying to see, are these Yi values above or below their respective means, meaning are they above or below Y bar? So you're looking at your observations and you're looking at these X and Y values and you're trying to see, are above average values of X observed above average values of Y, and that will be a positive correlation. Larger values of X observed with larger values of Y. And then you're also trying to see, are below average values of X observed with below average values of Y, then that's also a positive correlation. Right? So smaller values of X with smaller values of Y, and larger values of X observed with larger values of Y. That means that as X increases, so does Y. So that's a positive correlation. And then you're also trying to see what's happening in terms of, are they on opposite sides of their means, meaning are larger values of X observed with smaller values of Y, meaning as X increases, Y decreases. And you're looking at all of these things, right? So covariance, this is what covariance looks at. Does Y increase when X increases, or does Y decrease when X increases, right? So that's what covariance looks at. It compares the X values that you observe in your data set to the X bar value, and it looks at the Y values in your data set and compares them to the Y bar value. So that's because you compare them to their respective means, so you can understand whether it's a high value of X and Y or a low value of X and Y. That's why you compare them to their means. And that's what covariance does. What does the variation of X and Y look like for each observation? Again, are larger values of X seen with larger values of Y or not? And then again, it's just to answer the question, is Y increasing as X increases, or is Y decreasing as X increases, right? So that's what covariance looks like. So that's why if you have that they're moving in opposite direction of their means, meaning as X increases, large values of X, Y decreases, small values of Y, covariance will be negative. You will get a negative value for covariance because they're moving in opposite sides of their means. So that's what gives it that negative value. But if they were moving in the same direction, as X increases, so does Y, then because they're moving in the same direction, you would end up with a positive value for covariance. And if the same thing, if X decreases, so does Y, they're moving in the same direction, both moving below their respective means. And that would again be a positive value. So again, covariance is positive or negative depending on is Y increasing or decreasing as X increases, pretty much, essentially. So that's why SXY can be positive or negative, right? Depending on whether Y increases or decreases as X increases. And so I'm just reading the chat. So there was another question added to the chat. Yes. So in this case, the question says, if SXY is equal to 28,625, is that a positive correlation? So in this case, yes, it is a positive correlation because this is a positive value, but it's difficult to interpret covariance. It's difficult to interpret, sorry, let me share. Actually, I don't need to share that, right? So when you're looking at numbers like this, 35,657, it is actually very meaningless to interpret this because you're going to be getting different values for covariance depending on how many observations you have. The more observations you have, the larger this value will be automatically. And it also depends on the units of your X and Y variables. For instance, our cigarettes variable, is it measured in number of cigarettes or number of packs of cigarettes? Or dozens of cigarettes? How are these variables measured? So again, depending on the units, you're gonna get different numbers. So that's why we can't really interpret this number in a meaningful way. So that's why we turn to B1 instead, right? So again, B1 is a measure that is dependent, that is determined by covariance. But because covariance is difficult to interpret, we take this number and we turn it into B1, and B1 is much easier to interpret. So again, you won't be interpreting SXY except to see whether it's positive or negative, meaning whether you have a positive or negative correlation, but it is not that, it's not a good use of your time to try to interpret this actual value, right? So again, all you have to do is it positive or negative, and that's it, and then move on to B1 and our Pearson's R, which are a much better way to interpret covariance. Okay, so let's move on to, so I've already determined, I already just demonstrated this to you guys. So now let's do the other formulas that we've seen last class. So we also saw these, so we saw SXY over SXX, and then we saw this formula linking B1 to R, and then we saw these formulas as well. So now I'm going to be working with these formulas. So here what I've done is B1 is equal to SXY over SXX. So this one here uses this formula right here. SXY over SXX. So essentially, this 28,000 divided by 96,000. And that's essentially what RStudio does to get the B1 value that it reports to you when you run your command. So this is the same exact calculation that RStudio does. SXY divided by SXX gives us the 0.2955 that we saw in RStudio. So let me go back to RStudio. So now, this is the four. So this is here, SXY over SXX. So that's precisely what I've done here. And of course, when you're doing the homework, you don't need to manually calculate these. In fact, you shouldn't manually calculate these things. But I'm doing this right now to show you where the B1 value that you get comes from. Right? So again, when you're doing the homework assignment, I don't want to see any manual calculations. I want you to instead use this command. So remember that we created our list that includes all of the information from the linear model. And we use the coefficient command to give us the regression coefficients, B1 and also B0, right? So this is B1. And RStudio got this value precisely by doing these calculations here, SXY over SXX. Okay, so now, and of course I already showed you guys how you can do it like this too. So this is simply the command for covariance divided by the command for variance of X. You can also do it like this. Okay. So now let me go back to that PDF file. So now I want to work with the relationship between R and B1. So here, the next formula that I'm using is this one. R is equal to B1 times SX over SY. So and that's precisely what I've done. R is equal to B1 times SX over SY. And when you do this calculation, you get 0.8, right? The very strong correlation that we saw last time. And again, this is exactly how Pearson's R is calculated. Of course, there's another way. So again, I showed you guys how you can take this formula and turn it into this formula. All you have to do is substitute this for the B1 here and do some canceling, and you end up with this. So SXY divided by the two standard deviations. And this is what I've done here. SXY divided by the multiplication of these two standard deviations. And again, you get 0.8, our very strong positive correlation. Okay, so because, the reason why I'm taking the time to show to show you guys these calculations is that, so again, statistics, quantitative methods is statistics, and statistics is very, very similar to math, right? So when you're learning math, you learn one concept, and then you build on it, and then you keep on building on it until you move on to more difficult, more complex concepts. And here it's exactly the same thing, right? So Sx and Sy, for instance, those are things that we learned when we were doing univariate analysis. So those are some of the first things that we learned. And now we are applying those concepts to bivariate analysis and correlation measures. So everything is interrelated. So at the end of class today, we'll be doing some exercises to really help you see by doing calculations how every single thing that we've learned so far is interconnected. Okay, so now what I want to do is start talking about our last measure of correlation. So that is R squared. So now let me go to the whiteboard. Okay, so R squared. It is the coefficient of determination. It is another measure of strength. But whereas Pearson's R was a more direct measure of strength, you can interpret R squared to be a more of an indirect measure of strength. So because remember what I said last week, Pearson's R only looks at the scatter plot. B1 looks only at the best fit line and the slope of it in particular. And R squared combines the two, right? So R squared looks at the relationship between the scatter plot and the line, the best fit line. So in particular, it looks at how well does the line fit the scatter plot. So in order for the line to fit the scatter plot well, you need a strong measure of R, meaning, so R looks at only the scatter plot. So it is really the shape of the scatter plot and how tight or loose the scatter plot is that determines how well the line will fit the scatter plot. So in order for R squared to have a good fit, Pearson's R must be a strong value, right? So whether it is positive or negative, it must be a strong value, meaning you must have a strong correlation between X and Y. So when that correlation is strong, then you will end up with a very tight scatter plot, and that is what will allow the line to fit well. So that's why it is an indirect measure, so to speak, because in order for the line to fit well, the scatter plot must be tight rather than loose. Okay, so now what I want to do is focus on, let me draw two scatter plots here. And one of them will be strong and one of them will be weak. All right, so let me do this. Okay, so I'm just drawing a weak correlation for now. So again, assume these are all dots. Okay, so here is a positive correlation. And at the x-axis, we have the x variable. And then for the y-axis, we have the y variable. So again, in this case, because we can make out a linear trend, but again, it's a loose scatter plot. So here, it is upward sloping, meaning as x increases, so does y, and as x decreases, so does y, right? So these are the small values of x are observed with small values of y. And then here you have the large values of x that are observed with large values of y. So that's the covariance, right? Our small values of x observed with small values of y, and our large values of x observed with large values of y. If the answer to those questions is yes, that means that the covariance will be a positive value, and that's why B1 and Pearson's R will also be positive. So here you have a loose correlation. And now let me draw a stronger correlation. So I'm still going to make it positive just so the comparisons become easy. Okay. So again, it's the x variable and the y variable. And then let's draw the dots. So again, much closer together. Why is it so hard to draw this? Sorry, it's like, okay. Okay, so now you have this correlation here. That's still positive. It is still upward sloping. As x increases, so does y. And that means that covariance is positive, and B1 is also positive. Okay, so here again, you see that there is a tighter scatter plot, and here you have the looser scatter plot. So that's why here, Pearson's R on the left-hand side will be less than the Pearson's R value on the right-hand side, because there is a stronger correlation here, and it's a positive correlation. R will be closer to +1 here, and here R will be closer to 0. So that's why Pearson's R value here is less. And if I were to add the line, the best fit line to these, so let me add it in a different color. Let's make it blue. That's what it looks like on RStudio. So now let me add the best fit line here. So again, it's supposed to go right in the middle, right? Because it is an average of your line, so it should be right in the middle of your scatter plot. And in particular, it needs to be as close to every single observation as possible, right? Because the best fit line minimizes the sum of squared errors. And then let's draw it for this one, the scatter plot. Right, so again, it should be as close to all the observations as possible. So now we have the two scatter plots with their respective best fit lines. So as I said, these are both best fit lines because even though this one looks like it's a lot closer to all of the observations, this line still minimizes the sum of squared errors in its own scatter plot. And this line minimizes the sum of squared errors in its own scatter plot, because again, we're not comparing across different scatter plots when it comes to the best fit line, right? So this is the best fit line for this scatter plot, and this is the best fit line for this scatter plot. And remember that we've already talked about the sum of squared errors, right? The best fit line is the line that minimizes the sum of squared errors. So that means that the line is as close to the observations as possible. Right, so minimizes the difference. So again, this is minimizing the difference between line and observation. So now what I want to do is revisit our notation. So remember that sum of squared errors, EI, and then we were squaring this, right? EI, squaring it, and then sum, adding it all together. So let me add that sum. Oops, that's not what I wanted. The sum signal. Oh, it's blue. I don't want blue. Oop, that looks terrible. Okay, there we go. The sum of squared errors. So this is minimized. So this is our starting point for R squared, right? So this is the distance between line and observation. And we also saw the formula for this, right? So it's all about yi and y hat I. And here the formula is yi is first, right? So ei equals yi minus y hat I. And of course, the sum of squares. So we do this for every single observation. So again, because I have more space here, I'm going to be demonstrating it here rather than here. So now let's do it in red, a different color. So now when it comes to every single observation here, I'm going to be looking at the vertical distance. Oops. Right, so here's the vertical distance, here's the vertical distance, here's another one, etc. So you do it for every single observation. Right, so every single observation. Oh, this one is already on the line. So this observation, yi equals y hat I in that case, right? Right, so again, you do it for every single observation. Some observations are closer to the line compared to others, right? Doesn't matter because it's the average that counts. Okay, so you're doing it for every single observation. And each of these red lines that I drew is an EI, right? So each one of these things is an EI. So this is one EI. So this is the EI. For this particular observation, it's a negative EI because it is below the line. And this is another EI here for this observation right here. And it is a positive EI because this observation is above the line, etc., etc. So all of these observations contribute an EI value. And we square them so the positive EIs and the negative EIs don't cancel each other out, and you'll end up with, because remember, this is a line that is an average, it's right in the middle of your scatter plot. So the positive EIs will be exactly the same value as the negative EIs, right? So that's what it means to be right in the middle. If you do not square them, the positives and the negatives would cancel each other out. You'd end up with 0 sum of EIs, when in reality, there is absolute distance. So that's why we square it. So we end up with, we can account for the absolute distance between line and observation. Okay, so you do this for every single observation. You calculate the EI for every single observation. You square it for every single observation. And you add together all of these squared values. And then that's what gives you sum of squared errors. So right, so simply the sum of squared errors is going to be this distance squared, and you add it together for every single observation. So now I'm going to give this another name. I will call this SSE. So this is going to be the terminology for sum of squared errors. We're going to call it SSE for R squared. And I'll tell you guys about what SS and E and all of those things stand for in just a few minutes. So now I'm going to take this scatter plot and all the EIs here and compare it to this one. So now, because here, every single observation is close. I mean, I shouldn't say every single observation because this is right on the line here, but you have observations in general that are closer to the line here compared to this scatter plot. Because this is a tighter scatter plot, observations are closer to the line. And because this is a looser scatter plot, observations are farther away from the line. So now let's take a look at the EI values here. Right, so here's an EI. Here, oops, here's another EI. Here's another EI. Here's another EI, etc., etc. You're drawing all of the EIs, and you see that the red lines here are much shorter than the red lines I drew on the left-hand side. Right, so here the EIs are much smaller. So that meets that. So here, now I'm going to be comparing the SSE values. Because I'm adding together a whole bunch of small EI values, right? If you square a small number, you get a small number compared to what you have here. And you're adding together a whole bunch of small numbers. So it's going to be the case that the SSE here is going to be small, because the EI values are small in absolute terms. Right? You have small values here for each observation. Square a small number, you get a small value. That means you're adding together a whole bunch of small numbers. So SSE here is going to be small. And then here, SSE is going to be larger. Simply because all of the EIs are larger, there's more, because the scatter plot is looser, the observations are farther away from the line compared to the right scatter plot. Because the observations are farther away, you end up with EI values that are larger in absolute terms. Right, so you take these larger EI values, you're squaring large values, you end up with large values, you add together a whole bunch of large values, you end up with a large SSE. So when it comes to a looser scatter plot, SSE will be larger. But again, remember, this is still the best fit line, right? Just because this SSE is larger compared to the SSE on the right scatter plot doesn't mean that this is not the best fit line. This is still the line that minimizes this value, the SSE value, for this scatter plot. Any other line would end up with an even larger SSE here. So this is still the best fit line. It still minimizes the SSE value, but because this is a looser scatter plot, here the SSE is larger than the SSE from this scatter plot. Okay, so now I want you guys to look at SSE. Stands for, so I want you to consider this E here, EI, E, and then this letter E here, E for error, but the more correct term is residual. Right, so the more correct term is residual. So residual is simply the distance between line and observation, right? So E for error, but it is technically called a residual, right? So residual is simply distance between a line and observation. And so meaning how far the model is. So this is our statistical model. This is our regression model. So this looks at how far our model is from the actual data. So SSE, you can consider it as, given that you have your statistical model or regression model that is represented by the blue line, it actually, the EI value, the SSE value, measures how well your model does in explaining the data. Meaning if your model is close to the data, then it does a good job of explaining your data, right? Because we don't want to model a statistical model that is irrelevant to the data, right? We want our statistical model to do the best job that it can in explaining our data. So that's why it's the best fit line, right? But some best fit lines do a better job compared to other best fit lines, right? So measures how well, but it's actually the inverse of it, how well your model does in explaining the data. So it's the inverse, because the better it does, the smaller the SSE value, right? So it's the inverse. So if SSE is large, then your model doesn't do very well. If your SSE is small, then your model does very well. Okay, so now I'm going to be talking about variance for a minute. So let me draw another, scatter plot, but I'm going to be doing it slightly differently. So, so I won't be drawing the best fit line here. So I'm just going to take a random scatter plot. Again, forget about whether it's a strong or a weak correlation. So just some random scatter plot here. So let me draw the points. Okay. Okay, so now this is our scatter plot. And remember, so now in order to interpret this scatter plot in the new way, I'm going to be going back on a concept that we learned earlier on the semester, and we still mentioned it at the beginning of this class. So now this is our scatter plot. So remember what variance was, right? So variance, it was average variation, right? So average variation, because what made it average was that we took total variation and divided it by the number of observations, right? So you take total variation and you divide it by the number of observations. Well, n-1 really, if you're looking at a sample data set, right? So the fact that we are dividing it by n-1, that's what makes it average variation. So now I want to focus on total variation for R squared. Total variation, meaning I will take out this denominator. I will no longer divide by n-1. So remember, do I have the formula sheet? So let me open the formula sheet to show you guys that. Actually, it may be, sorry, just give me a minute so I can find that formula for variance. I don't have it on this document, the PDF file. Or I can just type it right now instead of wasting time looking for it. Okay, I'm just gonna, it's gonna look terrible, but I'm just gonna type it now. Okay, you guys can see the whiteboard, right? Just making sure that I didn't do something where you can't see what I'm doing here. Okay, perfect, thank you. Okay, so total variation. So let's remember what the SYY formula looks like. So now the reason why here I will be focusing on SYY is because the whole reason why we are doing quantitative methods, statistical analysis, looking at correlations, is that we're trying to explain the dependent variable, right? So our whole goal is to explain the dependent variable, what causes the independent variable, how much of an effect does X have on the dependent variable, what is the strength of the relationship. So here I'm going to be focusing on SYY, meaning variance of Y, because our whole goal in doing all of these correlations is to explain Y, explain the outcome. I cannot spell. Right? And our outcome is the y variable, right? So that's why we're going to be doing these interpretations in terms of y. And that's why here, when you were looking at EI values, we were also looking only at y, right? So just because we are trying to explain, our goal in this research project is to explain the y variable, the outcome, and we use x to explain y, but the point remains that we're still trying to explain y. So that's why our focus with r squared is going to be entirely the y variable values. So that's why SSE is calculated using yi and y hat I, and then the rest of the calculations I give will also be in terms of y. So that's why here I will be focusing on the variance of y. So now, because we are, we want to explain the outcome. We want to explain the y variable, and we are trying to explain it using statistics, right? So that's what we are doing. We are trying to, so again, in your theory, you'll try to explain it using words and paragraphs, and you'll have a story that links your x variable to y. But when we're trying to test that relationship, and when we're trying to explain that outcome y variable using quantitative methods, we explain y using statistics. So that's why explaining y in statistics means variance. But instead of variance, I'll be focusing on total variation of y. So that's what it means to explain your dependent variable, explain the outcome in statistical terms. So given that your dependent variable varies by a total amount, how much of that variation is your model able to account for? Right? So again, this is our starting point. Given that your y variable varies by some total variation, some total value, how much of that variation is your model? And remember, your model is made up of your x variable, right? So if you remember your best fit line equation, y equals b naught plus b1 times x, right? So explaining your dependent variable is done. Your model is made up of an x variable. So how well does your model explain your dependent variable, the variation in your dependent variable? That's the same thing as saying, how well does your x variable explain the variation, the total variation in your dependent variable? How well does your model, meaning which contains a single x variable, explain y? And we'll be looking at this, we'll be determining this in terms of total variation. How much of the total variation in a y is your model or your x variable able to explain? So now let's focus on, so let me write that formula, right? So SYY, right? So remember, you have yi minus y bar, the average y value, squared, and then you divide it by n minus 1. So let me, right? So you divide, do this division, but it is a sum. Oops, it is a sum. Right, so this is, oops, that's not what I wanted to need to be here. Right, so this is the variance formula, right? So this is what we had, and this sum actually looks terrible. Let me draw it again. Well, it's a slightly better. Okay, all right, so this is the variance formula. It is average variation. But now if I were to get rid of the denominator here, I end up with total variation. So get rid of the denominator and you end up with total variation, which is just this numerator part. And then let me add the sigma here. So this is what we're interested in. Given that your dependent variable varies by this much, how much of this variation is your model able to account for? So now total variation, if I were to represent this visually, so let's say this is the y variable on the y-axis, right, the y values, and then this is the maximum y value, and this is the minimum y value. Let's say that just by eyeballing it, let's say that y bar is somewhere here. I don't know, again, I'm not, again, this is just eyeballing. Let's say that y bar is somewhere here, right? Maximum y value, minimum y value, the average is going to be somewhere in the middle. So now I'm just going to actually extend this line, and let me just do it a different color. So let me do this color. Okay, so this is the y bar value, which I am extending all the way through my scatter plot. So now when it comes to total variation, all you're doing, again, it's vertical. We're looking at vertical distance. This is the y bar value. And then now you're comparing all of these distances between a line and mean value, right? So you're looking at all of these distances here. So this is the total variation in your dependent variable, et cetera, et cetera. So again, all of these distances, again, yi minus y bar, again, you square it because these are positive values and these are negative values. So you square it. So again, the positives and the negatives don't cancel each other out. And then you add it all together for every single observation and you get the total variation. So again, this is the total variation of your dependent variable. How much of this total variation is your model able to account for? So now what I want to do is, suppose this is the total variation in my dependent variable. It is this much. I'm going to split it up into, well, for now, it's not necessarily in the middle, but for now, I am splitting it into 2 equal halves. Again, that's not going to be the case. So this entire circle is total variation in y. And some of that variation, your model will be able to explain. So this is the portion of the total variation your model is able to explain. And then the remainder is simply the portion that your model is unable to explain. Right? So again, there are only 2 portions. The part that is explained and the part that is not explained. Portion of the total variation. Of course, total variation, but of course I mean total variation in y. Your model is unable to explain or account for. So we've already seen this. The portion of that total variation that your model is unable to account for. So this circle, so let me, before I do that, the circle is made up of these values, right? you calculate these differences, you square them, add them all together, you end up with this circle. And then the right half of that circle, the portion that is not explained, is the EIs. So remember, again, the correct term is residual, but think of it as E for error. So this is the error in your model, right? So again, this is the error in your model, meaning what your model is unable to account for. The portion of the variation in your dependent variable that your model is not able to account for. So that means that this is going to be, and let me just change colors here, SSE. This is the portion of the total variation in your model that, in your dependent variable, that your model is unable to explain. So again, think of it as, again, as I said, residual is the correct term, but think of it as E for error. And then total variation is going to be known as SST. T for total, E for error, and what do the SS values stand for? So SS, it's not Nazi Germany, it is sum of squares. Right? SS stands for sum of squares. So now let me rewrite these formulas for you. Sum of squares, SST, I already wrote it in the previous one page. It is simply yi minus y bar, square it, and then add it together. Yeah. Okay, sum of squares, sum of squares. That's what this SS stands for. Sum of squared errors, because this is, oh, sorry, this is, I just realized that I did SSE when in reality I should have done SST here. Sorry, just scratch that last minute of what I just said. It's gonna do exactly the same thing. I'll start with SST. That's what I meant to write. And that's the actual formula that I wrote. But I meant to write SST here. Yi minus y bar. And that's exactly what I wrote. Sorry about that. Okay. This is SST. Right? This is exactly what I wrote down here. Total variation. Right? So this is the same exact formula. Square it and then add it all together. Sum of squares, again, same thing, squares, and then you're adding it all together, sum of squares. And then here the T stands for total. Total sum of squares. That's SST, the total variation in Y, and it is simply SYY without the denominator and minus 1. Total variation in Y, total sum of squares. And now let's do SSE, sum of squared errors. So again, sum of squares, sum of squared errors, E for error, but residuals, as I said, is the more correct terminology. So that is yi minus y hat I. And again, we are squaring this. And then we are adding it all together. Sum of squared errors or residuals. So those are the two formulas. So again, this is what your model is unable to account for, the portion of the total variation in Y that your model is unable to account for. And then the left part is the portion of the total variation, the portion of SST that your model is able to account for. So now think of R here. So again, it gets a little bit confusing because you may see some variation in the letters that different books use. Sometimes you'll see that this might change to M for model, or this might change to R for residual. But this is the most common one that you see, SSR, R for regression model. So SSR, sum of squares, so again, this is the portion, so R for regression model. All right, so this is the portion of SST that your model is able to account for. And SSR is simply, well, actually, let me say SSR plus SSE equals SST, right? So these two portions add up to the total. SSR plus SSE is equal to SST, or in other words, SST minus SSE gives you SSR. So let me give you guys the formula for that as well, SSR. So again, don't worry about, again, I'll give you guys the mathematical proof if you want it. So SSR is simply this minus this. Okay, right, SSR is simply SST minus SSE. And again, don't worry about it, but if you do the proof, you end up with the following formula for SSR. Y hat I minus Y bar squared. And then you are squaring it, or adding it all together. So this is the formula for SSR. Okay, so now let me draw. So again, this circle, as I just put it in the middle, but as I said, it's not going to be always in the middle. So now let me go back to, actually, let me go back to here, these two scatter plots. So obviously, given that you have a certain total, you can have that SSE portion be smaller. And if you make SSE smaller, that means you are moving the line to the right, and that'll give you a SSR value that is bigger, right? So for instance, so let's take these two circles. So it might be the case that you have something that looks like this. And here you have SSE. And then SSR is right here. And you might have the complete opposite scenario where SSE is large relative to SSR. So now in this case, you see that in the top case, SSR is greater than SSE. And then here is the complete opposite. SSR is less than SSE. And here I made them roughly the same, right? So here I made them roughly the same. So these are the three possible scenarios. So now let's see which one applies to. So again, this is not applying to either one of our scenarios. I'm going to be looking at these. I'm going to be looking at these circles when I explain these two scatter plots. Okay. So as you are seeing in the left scatter plot, the errors are larger. So here, SSE is larger here compared to the SSE on the right-hand side. So I'm going to add to the bottom, SSE here is larger compared to SSR. Oh, sorry, what am I doing? SSE is larger than the SS. So again, the SSE here is larger than the SSE here. And then if I were to go here, so the left scatter plot looks more like this. The SSE is larger compared to the SSE that you see here. And if you have a large SSE, then you have a small SSR. And if you have a small SSE, then you have a large SSR. So now let me add that. Here, the residuals are bigger, so the portion of the variation, total variation in Y, not explained by the model is larger compared to this one. All right, so that's why the SSE is larger here compared to SSE on the right-hand side. And that means that if the error portion of the model is larger, then the model, regression model portion is going to be smaller compared to the right-hand side. The SSR, because the error is smaller here, then SSR will be larger. So the stronger the correlation, meaning R here gets closer to +1, the smaller the SSE and larger the SSR. So everything on the right-hand side here indicates a strong correlation. Right, so all of these here are indicative of a strong correlation. Oh, I should have chosen a different color. Do green. Right, so all of these here are indicative of a stronger correlation. And it's precisely because you had a very tight scatter plot to begin with. The tighter the scatter plot, the closer your best fit line. And again, best fit line represents your regression model. The stronger the scatter plot, the tighter the scatter plot, the closer your model, your best fit line will be to the scatter plot, the dots, the observations on the scatter plot. So that's why R is larger, closer to 1. And that is precisely what makes SSR larger and SSE smaller. But here, because R is smaller, it's closer to 0, you have a loose correlation to begin with. So when you put your scatter plot, because you had a looser scatter plot to begin with, when you put your best fit line on that scatter plot, the scatter plot will be naturally farther away from your observations compared to the right-hand side. Because R is a smaller, weaker correlation, closer to 0, that means that your best fit line is farther away from the model, meaning the error is larger. But that also means that your model doesn't do as well a job of explaining your dependent variable, Precisely because your model with the X variable is farther away from your observations. So now here you have everything that is indicative of a weaker correlation. It is because of smaller r that you end up with a large SSE and a small SSR relative to the right-hand side. Right, so these are indicative of a weaker correlation. So that means that you're gonna, right? So again, this is, I'm gonna add this. That means that your left scatter plot looks more like this. All right, so this is what your left scatter plot looks like. And then this is what your right scatter plot looks like. Okay, so now what I would like to do is go back to RStudio. So again, so today we don't actually have a lot to do with RStudio. The only thing we have to do is learn the R-squared values. And actually, before we do that, let me tell you what the SSR, SSE, and SST values are, and then we'll actually, I think it's better to do that after the break and do it together. Okay, so now if I were to give you the SSR, SSE, and SST values, and I've already written them down here on that PDF file here. All right, so these are the SSR, SSE, and SST values from our cigarettes and mortality rate data set. And again, similar to covariance, right? So again, covariance was also a large value, and that was also difficult to interpret. It's the same thing with these values. You will get large values, and they will be difficult to interpret. So these are the values for our data set. And again, we're going to turn it into a proportion in order to interpret these, which is a much better way to interpret. Okay, so I'm going to go back to the whiteboard and write down this information there. So now moving on to our cigarettes and mortality rate data set. SSR, according to RStudio, is 200. SSR is 245,330.79. SSE is 135,354.28. And SST is 380,685.077. So again, if you were to take a look at this, it is, very difficult to interpret these numbers. Like, how do you make sense of such large numbers like this? So again, the first thing I want to do is compare SSR to SSE. SSR is larger compared to SSE. So if I were to draw that circle again, I know that for my cigarettes and mortality rate, all right, okay, it's not turning black. Okay, let me do it again. Okay, right, so this is my cigarettes and mortality rate data set. SSR is larger, and that's good. We want SSR to be larger compared to SSE. And let me make sure that I do the same thing. Yeah, SSE was on the right-hand side of the circle. So this is, oops, this is what it looks like. You have SSE on the right-hand side that is smaller compared to SSR on the left-hand side. Okay, so now let's turn this into a more meaningful interpretation. R squared is actually, again, what we are interested in is SSR, because remember, R stands for regression model, and this is the portion of the total variation in your dependent variable that your model is able to explain. So this is what your model does well. This is what your model explains, the portion of your dependent variable that your model explains. So, ooh, let me see. There. This is what we are interested in. We want SSR, but because we can't really interpret 245,000, we're going to turn it into a proportion. And that's what SSR does. Instead of saying the portion of SST that your model explains, we're going to say the proportion of the total variation in your dependent variable explained by your model. Meaning, we're going to be doing R squared as SSR. So again, this is what we're explaining, what we want to focus on. That's why it's in the numerator, divided by SST. So we simply take this number, SSR, and divide it by SST. So because we are turning SSR into a proportion, R squared, so let's talk about the limits of R squared. So because it is a proportion, it cannot be negative, because you can't have negative proportion. It will always be some positive value, but because it is a proportion, it will range from 0 to 1. Unlike Pearson's R, which could go all the way to -1, R squared cannot. It will range from 0 to 1. So now let's calculate our R squared value. And let me actually also add that R squared is a proportion. So now let's calculate it. 245,330.79 divided by SST, 380,685. And let me make sure that I don't have a mistake with my decimal places, because I wrote these two in 2 decimal places, but for some reason this is written in 3 decimal places. Let me just double check that I didn't do a typo here. Okay, it's fine. Yeah, because I found this by another way. Okay, it's fine. Oh, it's 0.7. That's the mistake. It's 0.7, not 0.77. It's 0.7. Okay, so we do this calculation and we find 0.64. That is the R squared value. This is a proportion. So now you can just simply turn it into a percentage. Oops, 64%, right? Same thing. So now let's interpret this. 64% of the total variation in mortality rate is explained by the model. And our model is composed of a single X variable is cigarette consumption. So I can actually, so you can say 64% of the total variation in mortality rate is explained by the model, or because my model is composed of the cigarettes variable, 64% of the total variation in mortality rate is explained by cigarettes, the cigarette consumption variable. So this is how you interpret this, right? So we take this number and we turn it into a proportion, which is much easier to interpret than saying, okay, what is 245,330, right? So again, this is very difficult to interpret, but proportion or percentage is better. So again, 64%, it is bigger than 50% because I already knew that by comparing these two numbers. SSE was going to be smaller, the smaller part of the circle compared to SSR. So now one more thing we have to do is strength, because remember, R squared is still a measure of a strength. So we have to add the strength. And in order to add the strength, I'm going to introduce another final formula. If I take Pearson's R and square it, I get R squared, right? Pearson's R squared is the same thing as coefficient of determination. So that's why, depending on, so again, with statistics, notations do vary, right? So as I said, notations vary when it comes to SSR, SSE, but you'll also find that there's a variation in notation. Sometimes you'll see capital R squared, but sometimes you may see lowercase r squared to reflect the fact that it comes from Pearson's R squared. Okay, so now when it comes to strength, we will simply use the same cutoff threshold points that we used with R squared, Pearson's R. So remember, so right now I'm focusing on a positive correlation. So remember, one meant perfect correlation. If it was greater than or equal to 0.8 all the way up to, but not including 1, it was a very strong correlation. And it was, if it was greater than or equal to 0.6 all the way up to, but not including 0.8, it was a strong correlation, etc., right? So it's the same. These are the same things I gave you, the same thresholds I gave you last week, but this is for Pearson's R. But because Pearson's R squared is R squared, you can actually take this value and square it. 0.8 squared gives you 0.64. So that simply means that if R squared is greater than or equal to 0.64, then it is a very strong correlation. And then you would do the same thing. 0.6 squared would give you the threshold for R squared for what is considered to be a strong correlation. You do it again for 0.4 for a moderate. Do it for 0.2 to figure out the threshold for a weak correlation, etc., etc. So this is, these are the thresholds. But of course, one more thing that I'm going to say, by comparing, by looking at Pearson's R first, if you have already determined that with Pearson's R, right, so because remember it was 0.8, oh, I don't have it here. It was on the PDF file. Right, so we already determined that Pearson's R was 0.8. And based on the thresholds that I gave you, if Pearson's R is greater than or equal to 0.8, it is a very strong correlation. That means that if you found that by looking at Pearson's R, it's a very strong correlation, then R squared will also by default be a very strong correlation as well, because R and R squared take a look at the same exact correlation in the same data set between the same two variables. It's looking at two different aspects of the strength, right? So this looks at the scatter plot, And this looks at how well the scatter plot or the best fit line fits the scatter plot, but they're both measures of strength. They are both looking at the strength of the correlation between the two variables, the same two variables in the same data set. So that's why if you determine that by looking at Pearson's R, by interpreting it, you determine that it's a very strong correlation, then your R squared value will also be automatically very strong. And if you determine that Pearson's R is a moderate correlation, then by default, automatically, R squared value that you get will also be a moderate correlation, et cetera, et cetera. The strength interpretations for R and R squared will be exactly the same. So that's why, let me go back to the whiteboard. That's why I had determined that .8 is a very strong correlation. That means there's a very strong correlation between cigarette consumption and mortality rate. We can interpret R squared equals 0.64 to be very strong as well. Okay, so two interpretations, two things you need to include in your interpretations for R squared. This is the most important thing. Include how much of the total variation in Y is explained by X. 64% of the total variation in Y is explained by our X variable. But of course, don't just leave it at X and Y. Include all of that variable information. And then we can further interpret that there is a very strong correlation between X and Y because this is equal to the threshold for what is considered to be a very strong correlation. And you can just say that because Pearson's R was very strong, then this is also a very strong correlation. Okay, so that's it for R squared. Any questions about R squared? Nope. Okay, so let's take a 10-minute break and then we'll continue. So now after the break, let's open RStudio and I'll show you guys exactly where you would get this information from RStudio. All right, so I'll see you guys in 10 minutes. Oops. Okay, so let me share my RStudio screen with you. There we go. Okay, so now, again, it's only just a few short commands. So we've already learned how to do Pearson's R, right? So it's just correlation and you will do your X and Y variables. And then we already went through how R squared is simply Pearson's R squared. So with this command, we get Pearson's R, right? So this is Pearson's R. And, oh, sorry, let me just make sure I have access to my chats in case I get any questions, I can see them. Okay, so that's Pearson's R. So now if I were to square this, then I get R squared, so 0.64. So this is R squared, 64% of the total variation in mortality rate is explained by cigarettes. So again, let's get the SSR, SSE, and all of those informations, that information as well. So remember that we've already created our linear model. So we've created a list from our last session that we called LM. Oh, actually, I called it LM SIGS mortality rather than MR, right? So this is something that we did at the beginning, so right after the scatter plots, right, in order to get the coefficients. So this is what we use. Again, we're using the same thing. So that's why it's good to create a list. I mean, if you didn't create the list, right? It'll give you just this information, right? So for instance, I didn't create a list. I just said LM. If you don't create the list, it'll just give you the X bar, not X bar, sorry, B naught and B1 value. But by creating the list here, a lot more information gets stored in this list here that I'm calling LM6 mortality, right? So a lot of information gets stored here. So I can use it to pull not only the coefficient information, but other information as well, right? So again, I'm using exactly what I created last time, that linear model list. So again, whatever you called it, I called mine LM6 mortality, right? So whatever you called it, you put that in there. And then you write down ANOVA. So again, the V here stands for variance or variation, right? So variation, so that's why it's looking at SSRs and SSTs and SSEs. Okay, so now let's do that. So now, don't worry about this column. Don't worry about anything here except for this column. We'll learn about the other stuff later on in the semester. Again, the only thing I want you to worry about is this column. So this is the SS column, sum of squares. So this is the column that we want. And here you have residuals. So I wonder if this will allow me to copy and paste this onto the whiteboard. Let me see, let me experiment here a little bit. I wonder. No, it won't let me. Okay, never mind. Okay, so here, again, these are the only two numbers that I care about. So again, residuals, like here, you see that they are referring to residuals rather than errors. So that's why this is not SSR, but rather this is SSE, right? So when you do this ANOVA results in RStudio, the residuals are SSE. So SSE equals 135,354. And here you are given your model. Cigarettes, that is your model, right? Because remember, our model is made up of a single X variable, and that X variable is 6. So this is our model, regression model. So this is SSR right here. So this is SSR. And when you do ANOVA, it gives you SSR and SSE, but it doesn't give you SST, right? But of course, we know that SSR plus SSE is equal to SST. So we can do this calculation to find what the SST value is. 380,685, right? So this is SST. So now we can use the information from the ANOVA table in order to get our R squared value. So SSR over SST is R squared. So SSR over SST that we just calculated gives us R squared. So that's precisely what I'm doing here. And we get 0.64. Right? And it's the same thing that we got when we squared Pearson's R right here. Okay, so now one thing I want to do before our studio portion is over. So remember that last week, I showed you guys, okay, we do this, and then you can pull the coefficient information by using this command. And I also said that you can pull more information from this list by using different commands. Like for instance, you can get the y hat values if you use the, oops. You can get the y hat values by using the fitted command, or you can get more information by using the summary command. So now I'm gonna run the summary command. All right, summary of my LM6 mortality list. So this is what you will get. We briefly saw this last week, and I said that this is the only thing you have to worry about for now, B0 and B1. But you see that you also have R squared. Don't worry about adjusted R squared. Worry about multiple R squared for now. You have a multiple R squared, which is the plain old R squared that we just learned about. That is also reported on this output, all right? B0, B1, and R squared. So that is, so again, when you do use ANOVA, it doesn't give you R squared, but you already know what R squared is when you looked up your B1 and B0 values. It is reported right here. So as I said, don't worry about it. Again, you're seeing residuals, the minimum residual value, and that was the United States. The maximum residual value, which observation has the most positive residual, meaning which one is farthest away from the line, but above the line. And this one looks at which observation is farthest away, but of course below the line because it's negative. So you get residual information here, you get the coefficient values, and don't worry about these and this either. So these are, so we're gonna learn everything in this output, right? So because now we have learned how to describe our data, and then the rest of the information on this output is to do hypothesis tests with our descriptive statistics, right? We've described our data, and the next step is going to be to do inferential statistics, which is hypothesis testing. So the rest of the information on this output is all about hypothesis testing. So that's what we're gonna start. So we have to learn about distributions first, because we will be looking at distributions during hypothesis testing. But the first thing, actually, you know what? I don't know if I want to start distributions today, because what I want to do is do a couple of questions to solve. Because as I said in the beginning, so let me go back to the whiteboard. As I said in the beginning of class today, everything that we've learned so far is related, even the things that we learned in the first day of class, the second week of class, all of these things, they are still relevant, related to what we're doing today about the bivariate analysis, about the R squared and Pearson's R and B1 values. So everything is related to each other. Everything is connected. So now I want to do a couple of exercises, a couple of problems that show you how everything is mathematically related. So let me see, let me find, I have some problems for us to solve, but I'm only gonna solve one, and then I will give you guys class time. So meaning I'm not gonna just sit there watching you, because I can't even see any of you. I'm not gonna wait here while you're solving it. What I'm going to do instead is, after we solve our first example together, then I'll give you the two examples, two problems you should solve on your own. And once I do that, I will end the Zoom session, and you should take class time to try to work on these problems on your own. So again, it's not homework, it's not, you know, I won't be grading these or anything like that. But again, it is good practice, right? Because again, remember, you have a second midterm. And in the second midterm, you could get, because now that we've learned all three correlation measures, you are gonna get most likely a problem on the midterm that tries you to mathematically see how everything is related to each other. So now let's start with the first problem. And let me just make sure that I haven't missed any chats. Okay, everything is good. So now let's do, this is what I'm going to do. Okay, problem 1. So again, don't worry about the context of the question. Don't worry about what X measures, what Y measures, or anything like that. Suppose that these are the information that was provided. SY is equal to 9. SSR is equal to 720. N is equal to 10. And the question asks you, what is R squared? Okay, so now here we have the standard deviation of Y. Our sample is 10 observations, and we've been given SSR. So again, SSR has been given to us, but in order to interpret it in a meaningful way, we have to turn it into a proportion, and that's what R squared measures. Okay, so let's do it. All right, so we know that R squared is equal to SSR over SST, right? So we know SSR, but we do not know SST. So we have to first solve SST. So we know that the SST formula is yi minus y bar squared. Well, the sum. So let me add the sum here. And then we know that this is the numerator of SYY, right? So I said this is total, and SYY is a variance, and this is average. So this is the numerator of SYY, because we know that SYY is equal to YI minus Y bar squared n minus 1. Oops, not 2, n minus 1. So right, so this SST is the numerator of SYY. So which means that I can actually rewrite the SYY formula in the following way. SYY is equal to, so this whole thing in the numerator equals SST divided by n minus 1, right? So I can just simply rewrite the SYY formula that way, right? SYY is this divided by n minus 1. So now we can solve for SST using SYY because we have been given SY, right? So we can use SY, and we know that SY times SY equals SYY. So all we have to do is square this, and then that is SYY. So SYY equals 9 squared, or 81. So this is SYY. Okay, so now I plug in 81 to here. Right, so that's what I'm going to do. And I end up with 81 equals SST divided by n minus 1, and n minus 1 is 10 minus 1, because n is equal to 10. And then the final step is cross multiply, and we have SST. SST is equal to 81 times 9. And you get 729. But that is the final step in figuring out what SST is. So now we have SST. So now we can use this formula. R squared is SSR, which is given to us, divided by SST, which we just solved for. So let's just plug it in. Or 720 divided by 729. And when you do this calculation, you get that R squared is equal to 0.99. So let's interpret this. 99% of the total correlation in whatever the y variable is, we don't know, is explained by whatever the x variable is. And of course, this is greater than 0.64, so this is a very strong correlation between x and y. Okay, so now one thing I want to say is you can take this number and solve for Pearson's R, because remember, oh, sorry, I have a question. How did I get 720? So this is what I'm using. R squared is SSR over SST. SSR was given to us, right? So that's part of the question. It was given to us. SSR is 720. And then 729 is just what we solved for. Okay, so now let's try to solve for Pearson's R. So we know that Pearson's R squared gives you R squared. So in order to figure out what Pearson's R is, we can simply take the square root of R squared. All right, square root of R squared. So one thing when it comes to taking square roots, when you take the square root of a number, you have to set it equal to plus or minus. So the square root of 0.99 is equal to, equal to plus or minus 0.995. The reason why you have to put a plus or minus is that if you take positive 0.995 and square it, you'll end up with positive 0.99. And if you take negative 0.995 and square it, you'll also end up with positive 0.99. Right? Doesn't matter whether it's a positive Pearson's R or negative Pearson's R. If you square it, you will end up with the same R squared value. So that's why when you do the reverse, you take the square root, you have to say that, well, the answer is 0.995, but it is plus or minus. So anytime you take the square root of a number, the answer is plus or minus, right? Always plus or minus. So in this case, we know that we have a very strong correlation between X and Y. And we know that Pearson's R value is either positive 0.995 or negative 0.995, but we don't know which one it is. Because remember, there are three things that tell us whether we have a positive or a negative correlation. First thing is SXY. The second one is Pearson's R. The third one is B1. Right? So these are the three things that'll tell us whether it's a positive or negative correlation. But here, I have not provided any of that information. We know that we have a very strong correlation between X and Y, but we don't know whether there's a positive or a negative correlation. None of this information here tells us anything about the direction of the relationship. So if I were to try to solve Pearson's R, all I could say is that it is 0.995, but I can't tell whether it's positive or negative, meaning I cannot tell whether we have a positive or a negative correlation. So because we don't have these three pieces of information, we don't know whether R is positive or negative 0.995, right? So that is very important, right? So we can find R squared easily from Pearson's R, but it's not as easy to find Pearson's R from R squared because we simply will not know whether it is plus or minus. So here, if the question asks you, is there a positive or a negative correlation between X and Y, then your answer would be, I don't know. We don't have enough information to answer that question. But of course, suppose I gave you all the covariance was negative, or if I gave you from context, if I said, well, as X increases, Y decreases, from there, you know that it will be a negative correlation. So again, you can get not only these three pieces of information, but I mean, statistically, you need one of these three to tell whether it's positive or negative. But non-statistically, you can just look at the context. No, you don't need all three. So I have a question here. It says, do we need all three? No, just one of the three is enough to tell. So again, these three things tell us whether we have a positive or negative correlation. You don't need all three, because remember, if one of them is positive, then all three are positive. If one of them is negative, then all three are negative. So you just need one of these. So if I had told you that SXY is negative, then you would know, oh, it's negative 0.995 for Pearson's R. But you don't need all three. All right, so any other questions on this example? All right, so that's why, again, here, just let me go back to this scatter plot. I'm almost done. I'm gonna give you guys your problems to work on your in just a minute. So, Pearson's R tells us the direction of the correlation, meaning whether it's positive or negative, but R squared does not. So that's why we want to be looking at not just one measure of correlation. We want to do all three measures of correlation, because all three gives each one of the three measures of correlation gives us a different piece of information. So R squared doesn't give us direction, so that's why we still need Pearson's R. But of course, Pearson's R doesn't tell us how well our model does in explaining Y, right? So we want to know how well does our X variable does, because the whole point of us doing this research project, quantitative methods, is to explain Y. We first identify our X variable, and then we hope for the best that X does a good job of explaining Y. But of course, Pearson's R doesn't tell us that. Pearson's R doesn't really directly measure how well our X variable or our model does in explaining the dependent variable. So that's why, even though we have two measures of strength of the correlation, we still want both of these two measures because they give us different pieces of information, and these different pieces of information are equally valuable. But remember, both have the same strength, right? Meaning if one is very strong, the other one is also very strong. Okay. Yeah, so in this case, so I'm looking at the question again. So we don't have the value of R. So in this case, if I asked you, is this a positive or negative correlation? Then your answer is there's not enough information to tell, right? So if I ask you again, but we don't have the value of R to respond to your question. So in this case, yes, we do not have the value of R. We know what the absolute value is, but we don't know whether it's positive or negative. So if I asked you, no, we did not. This is R that we solved for, but either one is possible. We don't know whether Pearson's R is positive 0.995 or negative 0.995. So this is the R that we solve for. It could be two possible values, but we don't know which one it is. Okay, so I'm just looking at the chats really fast. Exactly. So we know the value, but we just don't know the direction. That's exactly right. Yeah. Okay, so now let me give you guys the problems to work on at home on your own, and then these are these two problems that I give you will be the first things that we do next week in the beginning. All right, so now the first problem, again, it's not homework. You don't have to do it, but it is highly recommended that you try these on your own because it will be good practice for the second midterm. So the first one is very similar to what we just did. So suppose that SY equals 10, SSR equals 400, N is equal to 11. What is R squared? That is number one. So now let's do, let me give you the information for the second one. So the second one, I'll be honest with you, it is more difficult. So it'll require you to do a lot more calculations than the first one. But then with the second one, you're truly realizing how everything that we've learned so far is connected. Okay, so here we do know R is equal to 0.8. We know that it is positive 0. So now we know that it's a positive correlation. SSR is equal to 95. N is equal to 11. SX is equal to 20. And B naught is equal to 2.1. So I want you guys to write the regression line or the equation for the best fit line, filling in the B naught and B1 values. Meaning, we know that it is yi is equal to B naught plus B1 times xi. So this is the best fit line equation. I don't need you to put X or Y information here. All I want you to do is fill in the B naught and B1 information. B naught is already given to you. So essentially, this question is asking you to solve for B1. Meaning, what is, essentially the question asks you, what is B1? So this is what you have to do, these two questions. Again, this will require a lot more calculations than you will need to do for question number 1. But again, do make sure to take the time to attempt it. I am giving you class time to do these questions. And if you attempt them on your own, again, you're going to get a lot of practice for the midterm. Okay, so that is it for today. Just a reminder that your homework is due tomorrow at midnight. And now you've learned every single piece of code that you need to know for the second homework assignment. So hopefully it should be pretty straightforward from now on. So before I end our Zoom session, so before I do that, let me actually save the whiteboard. Okay, good. So before I end our Zoom session, do you guys have any questions? Yes, okay, go ahead. I will do it probably tomorrow morning. Because I need to do some editing to it because I want to edit out the break because I think it may have shown your names while it was recording that. So I want to make sure that before I post it, I edit out the 10-minute break that we took. And I don't think I'll be able to do that right now. So I will do it first thing tomorrow morning. So you'll have all of this available tomorrow morning. Any other questions? All right, wonderful. So enjoy the rest of your evening, and I will see everyone next week. Bye, everyone.